Hello there. Welcome back to the AI Day Virtual Conference, brought to you by Embedded Computing Design. My name is Rich Nass, and I will be your moderator for this session where we cover intelligence moves out to the endpoint. This is actually a newer topic for us because it wasn't until fairly recently that there was enough processing power available to do any real computing at the endpoint. But that has clearly changed, as you will learn from our two expert presenters in just a few minutes. Hopefully you attended the previous sessions. One was AI at the edge and one was AI and vision. If you missed either of those, they are available on demand, as well as the first keynote address, which was delivered by Austin Ash, the worldwide head of AI solutions for AWS. So I encourage you to check those out. Before we move on, I need to thank our sponsors who make events like this possible. They are Acronix, NVIDIA, Intel, DFI, LIPS, Ambiq, Infineon, and Dedicated Computing. The session is being presented live. I promise you that. We are really here. And that means that you can ask your questions in real time. And we will answer those questions when these two guys are done with their presentations. And also stick around when this session is over. We'll be moving right into our second keynote, which is being delivered by Nick Gillian of Google. That takes place at 3:30 Eastern Time, just about an hour from now. The way that the platform works, you don't need to do anything. As this one ends, it'll roll right into the keynote. So you just sit back and it'll take you right into that session. And remember that all of these sessions will be available after we're done in an on-demand version. In addition to these live sessions that we're going through today, there are 8 on-demand sessions that look at all the different aspects of designing AI into your embedded system. They are very well done. Check them out. So this topic, as I said, is intelligence moves out to the endpoint, and our two expert speakers are first Carlos Morales. He is the Vice President of Artificial Intelligence at Ambiq, and then Venkat Mattela. He is the founder and CEO of Ceremorphic. They're a newer company. Venkat was the founder of Red Pine Signals before that, which was acquired by Silicon Labs. Before I bring Carlos out to start this off, let me just very briefly go through some of the housekeeping stuff. The two presentations together will take about 45 minutes. And that'll leave us some time to answer your questions. We'll answer as many as we have time for. On the right-hand side of the console, you'll see an area where you can enter those questions in real time. We tend to answer them in chronological order. So enter your question as soon as you think of it. Don't wait for the Q&A period to start. And if we don't have time to answer your question, somebody from one of the two companies will get back to you after we're done with the answer. So everything will be answered in some form or fashion. If you have an issue with the operation of the console, like the slides aren't advancing right, or there's a problem with the audio, put that into the question box and one of our technicians will respond with a fix. There's also a button up there that says handouts. If you click on that, you're able to download the presentations that these guys will be taking you through. Whew. Okay, that's it for me. All yours, Carlos. Take it away, please.
All right. Thanks, Rich. Thanks for the opportunity. Let me know if you can hear me before I launch into this. Give me a thumbs up on the console or something, or not. Okay, perfect. So my name is Carlos Morales, as Rich mentioned. I run the AI team at Ambiq, and I'm here to talk about the future of intelligent endpoints. And I'll kind of define that as we go through the slides. So I want, if nothing else, I want folks who are attending this conference to come away with 4 key ideas. One, the first one is a little counterintuitive, which is that AI is the easiest way to do hard things. And I'll get into what I mean by that soon. The second key idea here is that the endpoint AI world, this world where we're pushing AI right to the edge, right to the battery-powered corners of the planet, we're experiencing some major tailwinds, like good, positive, accelerating tailwinds, and I'll get into what those are. Something that's critical as we design AI systems that live out here is that the AI part is only a small portion of the entire problem. So you have to solve end-to-end, you have to have an end-to-end solution if you want to deploy AI at the far edge. And then the conclusion, which is really that AI is practical today. You are surrounded by endpoint AI today. It may not be as seamless as we want it to be. It may not be as efficient as we want it to be. But the fact that I was walking down an aisle at Costco the other day and there was an electric toothbrush that said AI powered on it tells me that we've reached ubiquity mode. We've reached this point where AI is actually forming a part of our day-to-day lives. All right, so let's launch into this first one, which is that AI is an easy button. It's counterintuitive because you heard for years that AI is hard. Doing AI is hard. You need experts. You need all this stuff. And it is a little hard, but it is the easiest way to do hard things. So the example I have here is computer vision. So object classification has been a problem for decades. We've been trying to solve since the days where you could actually get an image onto a computer, some computer scientist somewhere has been saying, what can we do with this image? Can we analyze it? Can we figure it out? Is it a hot dog or is it a cat? And so this is not a new problem. This problem's been around for decades. And if you look at this graph, which starts in 2010, think that 30 years before 2010, we were already trying to solve this problem. So countless graduate student hours hacking at this object classification issue got us to the point where you get 25% error rate, which is pretty impressive when you have the very general task, but is useless because if one out of every 4 pictures I show you, you misclassify, I'm just not going to use it. So fast forward to 2012, where the really big first famous model comes online. We called it AlexNet. And in a matter of a year or two, we went from 25%, 30 years of effort, down to 15%, and then 10, and then 8. And then we started beating humans at this classification problem. And that's what I mean. Object classification is misleadingly difficult. It is incredibly difficult. And the traditional way that we used before AI to solve these problems, the heuristic way where you're just adding rules and you have one grad student going like, okay, this is an algorithm for detecting edges, and another grad student saying, okay, this is an algorithm for measuring distance between 3D points, and just keep adding hundreds of thousands of rules like that. Toss that out. You come up with a very simple set of rules which define an AI model, the architecture, the layers of a model, and then you feed it billions of data points, or millions in the case of computer vision, and then you let the math figure out what the rules are. And so that works really well for computer vision, but it also works for every kind of fuzzy system. Time series, detecting whether there's an afibrillation going on in your ECG monitor, detecting if a plane is about to fall out of the sky because your engine is running. Those are fuzzy problems. You can write some heuristics to check. It turns out that AI is just a much more efficient way of doing it. So that's AI, the easy button. Oh, there's lag again, sorry. Okay. My next big point here is that there are some massive tailwinds that are really accelerating this space of AI, the endpoint AI space. I think the most important one is that researchers have started turning their attention to the small space. When I started in AI, the bigger, the more famous you were. Like the ResNets were huge back then. And then people just started adding parameters, and then BERT came along and GPT-3. And these are the things that made headlines and got you invited to NeurIPS. And you got to brag, Google got to brag about GPT-3 and billions and billions and now trillions of parameters. And that's where the research money went as well. There are a group of data scientists and researchers at MIT, Carnegie Mellon, and so on, that have turned their attention to the small. So they finally realized that to make this stuff practical, you have to start focusing on making things smaller. And there's a lot of progress there. There's a lot of algorithmic progress. There's a lot of compression progress. So we're looking at models that used to be megabytes are now kilobytes. You know, a typical speech recognition model is still in the megabytes, but a speech processing model could be 100, 200K, which is something that you can start thinking of as practical for endpoint. The other big kind of tailwind here is that the software stack has matured. If anyone was around in 2013, 2014 when this was started, it was kind of the Wild West. But with the advent of PyTorch and TensorFlow, and then the tool chains that you can build on that, and then you know, maintaining schemas and all this stuff, what happens when you have a mature stack is that an ecosystem can be built around it. So what we're seeing is a large ecosystem of endpoint software stacks. You see companies like Edge Impulse, which do AutoML on top of all that. And they're just reducing, this kind of software stack reduces the friction towards implementing endpoint AI. That's another big tailwind. And then the third one is, I think Rich briefly alluded to, it wasn't practical before to do this kind of, you know, processing at the far edge. But with the advent of, you know, something like a Cortex M4 is already sufficient for AI, but even more powerful processors, NPUs, and so on, plus you know, innovations in the very efficient power consumption space like Ambiq. This is now becoming practical. It's very nice to have a demo in the lab saying, "Hey, look, I can do speech recognition on a Cortex M4." If you're not able to do that for a month without killing your battery, then it's not practical. See, I'm learning to click once. All right, so why even do this, right? Why go through all the effort of compressing and putting these AI models onto your wrist, for example? And so it's useful here to compare, you know, the process, the kind of the life cycle of an AI inference using the traditional cloud-assisted AI, which is what happens when you talk to your watch or to your phone. You'll collect the utterance, you will do some pre-processing, and things are getting more sophisticated here, but you'll send it ultimately to the cloud for real processing, for language translation or for note-taking. These things actually go to the cloud. Even for simple things like controlling smart devices, often that does not happen locally. That happens all the way in the cloud, comes back. And putting aside privacy and security concerns, from a purely practical point of view, that's costing you seconds. And we've all had that experience when you're talking to your watch and it's something critical and you want to turn your lights on or turn off your security system and a packet gets dropped. And so now you're looking at 5 or 6 seconds of an alarm going off while you're going nuts. So you can't trust that. It's not quite practical yet. It's a good demo I'd like to show off to my friends, that you can operate my house using voice. But when I'm alone, I just turn off the lights with a switch because I know that will work every time. And then, of course, you're spending a lot of energy. The radio frequency transmission, even with BLE, is not that efficient. So if you're sending big packets of data, you're half a joule just to do an utterance, transmit it all the way up and then down. So what happens when you move that endpoint, that processing all the way out to the endpoint, if you're capable of doing that? It means that you have 100 millisecond response time. You know, hey, computer, turn off the lights, happens locally. So you're looking at inference time instead of cloud travel time, round trips. Also, the compute is comparatively negligible. It goes to zero basically compared to the RF power utilization. So we're order of magnitude more efficient, which is what Ambiq cares about. Ambiq is we're all kind of power obsessed. TANSTAFL, there's no such thing as a free lunch. So to do this kind of thing, you do need to move the processing down. You need slightly more powerful endpoints. You need more efficient endpoints. But clearly the benefits to your users and to your business are obvious. There we go. Okay, so I briefly touched on this. It's not sufficient to just do AI well in your device. And the reason is your device is now a standalone computer doing the whole thing. You're collecting the data, you're sampling audio, you're processing that audio, you're calculating Mel spectrograms and feature extracting, and then you do some inference, and then you have to do something with the inference. You have to transmit, you actually actuate, you have to do an alert, whatever it is that you're doing that inference for. And so when you take a big picture look at this, and I captured this last Friday, I was just doing some debugging for something called the speech to intent model. Speech to intent works by capturing 6 seconds of speech and then doing some inference to figure out what your intent was. Like the intent can be something like turn off the lights, turn the lights off, all those things turn into a single intent. And so just looking at this power graph, you can see that you're spending most of the time capturing audio, 6 seconds, and then 76 milliseconds inferring, right? So yes, you can see the power spike as you're doing the inference, because what I do there is I turn on our high power mode on the CPU, double the frequency, but it only happens for a very short period. So as a computer scientist, and you've all been through this, where do you focus your optimization efforts? Do you focus on the 6 seconds or on the 76 milliseconds? Now, we're kind of obsessive at Ambiq, so we do both, but you'll get a lot bigger bang for the buck if you focus on the 6 seconds. All right, so, and then AI is practical, and I can talk about all kinds of different AI tasks at the endpoint. But something that's very important for wearables, for talking to your watches or your rings or to whatever it is that you're wearing, is the user interface. These watches are small, they're hard to interact with. You're not going to be typing on them, and they're going to get more capable. So you will want a good user interface. And so a really practical user interface for these small devices is a microphone. Microphones are tiny, they're cheap, you can make them very low power. So a lot of these devices, the practical interface will be a speech UI. So here I kind of plot out 5 different kinds of speech UI, increasing in levels. Keyword spotting is something everybody's familiar with. It's the OK computer, and I won't say the real phrases because everybody's devices will wake up. It's a really well understood problem. It's been around for a while, since the Alexa days, the Siri days. And the really interesting thing here is that this task was actually designed to get around the low power kind of constraints. So let's call it unambitious. All it's looking for is a pattern, and it keys off of that spectrographic pattern and wakes up. And so you can do that very simply. There's a lot of devices out there that can do that. It's about 40K of non-volatile storage, and very little MOPS is millions of operations per second. So a Cortex M0 can probably do this. Can it do it efficiently and for months on end? Well, if you have a very good system, sure. But that's not ambitious. That's let's call that last year's state of the art. Things that are coming up now, speech to intent is an example of a command word interface. These are things where you're actually telling your phone to do things, right? You're telling your watch to do things. You're telling your fire alarm to do things. And so you need a little bit more than just the OK keyword, right? These models are bigger. They're 100K is a floor. They get pretty big depending on how much different kinds of intents or utterances you're processing, and they take a little bit more power. They're still eminently practical, right? You can definitely do this in a battery-powered device if you have an efficient battery-powered device. But now you start worrying about that battery utilization. All right. Like, do you leave that on all the time? How do you trigger? How do you turn on, turn off? Because you are using more compute power. Speech enhancement is something that we're using all right now. I mean, you're not talking back to me, but every day you're on a teleconference, there is a speech enhancement model running in the cloud. And what that does is it eliminates the noise, vacuum cleaners, leaf blowers. That kind of blocks that sound out. Think of it as noise cancellation for speech. It lets the speech through and nothing else. This is computationally intense. The difference between this one and the previous two ones is this is an online task. So it's running all the time. It's a streaming task, right? You have to do that all the time. So now, yes, the inference is about 5 MOPS, but you have to run it continuously. And so this is where you really start caring about how you use that battery. Still practical. And what makes it practical is also the memory footprint is not too onerous. It's 300 to 500K, depending on your accuracy. And we're seeing really good, by the way, this is one of the models that we're using to really kind of fine tune our compression. So we can probably get it smaller in 300K. And then the moonshots of the speech interface world are things like natural language understanding and processing. The top three, they don't know what you're saying, right? They just kind of key off of sounds, much like your dog does when you talk about food or something. The natural language processing and understanding models actually have a language model in them. And so even from a compute point of view, they're pretty intense, especially if you want them to be online. But the real limitation here is memory size. So the smallest models that I've been able to find are 25 megabytes. There's really good research pushing those down. But for most of our endpoint devices, 25 megabytes is still not realistic, right? Watches have a lot of megabytes actually. And you'll see some of the higher end watches, Wear OSs or the Watch OS watches will do natural language understanding. But the really far endpoints, the fitness bands and so on, those usually don't have that much RAM to spare, right? So practical, right? And this is how, let's wait for this slide to load. Okay, so this is how Ambiq does it, right? So Ambiq's flagship product is an SoC based on a Cortex M4, and everything in this chip is designed around ultra low power utilization. So for example, I've highlighted up in the green all the AI friendly features, but everything is AI friendly. But what I love about it, and the top one is the ability to switch frequencies dynamically. I can turn on the 100 megahertz and turn off the 200 megahertz, the clock doubler, every time I do a sample. So there's really no cost to flipping back and forth. There's probably a little bit of cost, and you'll have to kind of use that same power meter to figure it out for your application. The other thing that's really friendly for AI is the memory architecture, right? It has enough cache that you can do real compute. The TCM is fast and kind of chunky. There's a big chunk of TCM. TCM is a tightly coupled memory. It's an ARM kind of construct. But what I really love about this chip is the MRAM. MRAM is magnetoresistive RAM. Hard word to say. And it's non-volatile RAM that is based on the same technology that hard disks use, right? Giant magnetoresistance. But you cram 1 million of those things on a chip. So we have two megabytes of that. And what I love about it is it's as fast as TCM. It's indistinguishable from TCM when I'm running. I can put a model on that or put the model in the TCM and it runs about the same speed. So your application engineers will yell at you if you use TCM. They'll be a little bit more forgiving if you kind of stick to the MRAM. And then of course we have really efficient ADCs. Remember that 2 seconds, that what you're really running there is your ADC, and then you're kind of sampling. And in fact, there's a DMA engine that does the sampling for you. So what you really want to make sure is that your sensors being very efficient. So we do that as well. Okay. I think this is my last slide. I look forward to your questions after Venkat presents his presentation. And with that, it's over to you, Venkat.
Thanks, Carlos. Good morning, everybody. My name is Venkat Mattela, and I'm the founder and CEO of Ceremorphic. And thank you all for taking time for this presentation, and I'm very glad to be here. I have created the agenda for this talk today, and I think this Rich mentioned that I could talk about very little about the company, so I just have a very brief overview just to tell everybody who we are. But the 3 points that I'll be addressing in this talk. One is I'm talking about the reliable computing at the edge, the endpoint, and what is the driver for reliability requirement at the end device at the edge. That's the number one. And what are the challenges in challenges that creating the reliable computing at the edge? What kind of challenges it presents? And I also will be talking about the solution approaches that are being used in the past, as well as what is being proposed in our company. And I'll be talking about that and general approaches that are being pursued. Of course, we could have enough time for the Q&A at the end, and I'll be very happy to answer any questions if anybody has. So with that, the company, Ceremorphic, we founded in 2020, April. And of course, the development was going on 3 years before that. So totally company to date, we have 5 years of R&D expanded already into the company. And we are 150 full-time employees. We have an office in headquarters in San Jose and a development center in Hyderabad. We have gathered over 100 patents filed to date in this company, and 18 of them are awarded. This does not include some of the patents that we have licensed to from my previous company, which I sold to the Silicon Labs. Again, the Series A entire investment is from us, the founders of Redpoint Signals. And my manufacturing partners are TSMC, 5 nanometer access from TSMC, and just said the statue pack for the packaging. I just want to give you the history so that I'm sure there are a lot of entrepreneurs in this audience, and this might be something useful as well. The previous entity that I built, Redpoint Signals, is a wireless technology company, and sold it to Silicon Labs in 2020. So one of the things that I want to highlight is that anytime we come up with a differentiating technology, I can define this word called sustainable differentiation. That means you do something better than the best company in the industry by 1 times, 2 times, 3 times. And please remember that the company which is already the 90% market share or whatever the leaders, they're very qualified, highly qualified companies. They have a lot of money. And it is generally not going to be sustainable. If you try to do something at 2x, 3x, it's not going to sustain by the time you come to a level of trying to sell the chip or a system. So that's exactly what the previous one, the number one company in the wireless field, very, very well-respected company. I created a wireless solution which was 26 times lower energy. And then it becomes like, you have a very small chance. If you do something like that, you have a very, very small chance of selling. That means if you do 1 times, 2 times, 3 times, it's almost like you can pretty much take it from, whatever the industry people have done in the past, that it is not going to be sustainable. So take that input from this. But this is the company that we are running today. And I'm going to talk about the reliable computing at the edge today. So here I'm basically showing in terms of what is the reliability aspect and what are the drivers for reliability requirement at the edge or endpoint. And I did talk about this, but looks like there was a system error. But I'm going to show about the curve that depicts the reliability in a semiconductor product. That means there are 3 phases. Chips fail in the early part of the life. When you bring a chip, there is a manufacturing defect could be there. And during the system testing before we deploy, there are failures. And there is a deployment phase where there's a normal operation, and the failures happen, but these failures are much, much, much smaller. And the percentage of failure is much smaller. And there are a lot of mitigation technology in the software that can reduce the failures. Then you have the third phase where, aging, chips get aged similar to human beings and they start failing. So how do you really design systems, reliable systems, when the semiconductor manifests such a behavior? And that's basically the my today's talk about the reliable computing. And that's something that is a reality. It's happening today. And there are systems that is SOCs available today in reliable applications, like in automotives. So what is the really driver for the endpoint at the edge is that today, if you take the conventional computing, you have a sense, communicate, analyze, compute, and control. And if you take the real-time application as one dimension, and the AI that is becoming closer to the edge is another dimension. And as I mentioned earlier, I don't know how much of that was, I don't want to repeat, but what we are doing today in the artificial intelligence is a minuscule compared to what the human intelligence is, which is towards the general intelligence. And if you look at these dimensions of the device trying to become more intelligent, not just doing the object detection or object classification. In 2012, everybody got excited. 2016, still everybody's getting excited. But remember, this is all about artificial intelligence. There's no real intelligence in this. We're taking one application or one particular speech recognition. But if you have to do like a task like a human being, you need a lot more computing than what is even imagined today. So if that happens, the edge AI device is not going to need the current computing power. It's going to be orders of magnitude higher. Then on top of it, you add the continuous. Currently, the problem of computing is there only in the training. The problem of computing is not there today in the inference. It's very, very small computing. It's very well done. Like our previous speaker, very nice energy profile. Is a solved problem at the inference level. However, the training, your room size of computers working for 60 days. And guess what? If it fails one day, you have to rerun the training for next 60 days. There's a huge problem in the training. But if you take these three dimensions, real-time nature, artificial intelligence becoming more towards the general intelligence, and the continuous learning that is required everywhere. You don't want to wait for somebody else to learn and update the coefficients after 2 months. If you take those requirements, those are the drivers for thinking about reliable computing at the edge device. So that's about this slide. And what are the design challenges today? By the way, I'm very sorry that I was, if it is repeat for somebody, because I did talk about it for almost 5 minutes. I did not know that if there's a system error, but nevertheless, I think we are back on track. So as far as the design challenges are concerned for the reliability, today reliable systems exist in the in the world, in the industry. That if you look at an automotive, there are very credible companies make chips for automotives. That's why our cars run today very reliably. We're able to use them. However, the amount of computing power available in these chips is almost nothing compared to what is really required to do something intelligent task of autonomous vehicle or a driver as a system. The amount of computing that is required is a different order compared to what is existing today in a reliable way. And what is the techniques used in the current systems or the double, triple redundancy? What basically it means is you duplicate. For example, you have an aeroplane, you have a second engine. You put a logic, a second processor, a third processor. The probability of all of them failing is very, very less every time you add another one. And why do they fail? They fail because of something which is not in your control. It could be alpha particle, external radiation, or something could be environment could be different in terms of the temperature and the various other factors. So that is something, the existing mechanisms. And the existing mechanisms do have a recovery methods. That is, if you have multiple systems, if the failure happens, then obviously you know that at least I have a system that's working correctly because of you have a duplicator, a triplicated. But where do you start? And it's a very complex problem. So you have to figure out where to go from starting. You don't want to go to the time zero. Obviously, if you go to time zero, you're always correct. But a lot of state is lost and a huge amount of energy consumption, as well as some of the real-time responses could be completely off, where the system utility might be compromised. So that is one other challenge is the recovery. And the third one is the one, every time you do all these things in the reliability, it's very, very expensive in terms of managing for the size as well as the managing for the power budget. because once you build a reliability, that means you're talking about the second processing system, third processing system. If you are using this processor course from some other established IP vendors, you would see that whenever they give you a reliable processing core, it would be exactly 2 times the size, it'll exactly 2 times the power. So that's not real engineering. It's basically like, you can build a reliability by going 3 times, 4 times. Obviously, probably it will be less, but that's the current methods. So if you take in terms of a little bit low level, one more level, if you go, that is for example, the random errors. This is very important because that's where the real operation of your device is going to be. Whereas the early errors and the aging errors, they're something like what I would say is easier to manage with low cost. Everything is possible to manage. It's just we have to always be very, very careful about the cost. Because if I put 10 duplication, I can pretty much give as reliable as possible, but that's not physically possible. So here, the reason I'm talking about random errors is that this is something that very important because during the operation period they happen. That is because of the external radiation, alpha particles, or the environment that change. It's super important to reduce the failures, and you cannot avoid the faults. We don't control them, but you can always control the failure rate of the system. And these radiation, these external environment can result in permanent faults, or it could be a transient. It just makes the bit flip and go back. So these faults, when they happen, how do you really design the systems to mitigate? So that's all basically about my next thread. So far, we talked about what is the driving thing in the end device at the edge about reliable computing, and what are the challenges that reliable computing presents for the silicon engineering, and how do we really mitigate them? So the next slide is the one I'm talking about. Again, I brought back that slide where the life cycle of a semiconductor, early failures, a normal operation, and aging effect. And if you look at below that, you see a green line. Actually, that straight line is the business plan of my company. So basically, we cannot control the faults. We don't have the control over the faults. Faults happen, but I can always control the failure. That means, how do we really build a system? We cannot control the error. Something changed, an external temperature increased, a alpha particle came and hit a bit. Those I don't have in my control, but I can always make my system very reliable. So that's exactly what that curve indicates, where it says, I'm trying to bring the error failure rate to close to zero, and I have to do it zero. But it can be done today, even with the existing technologies, but it comes at a very, very high cost if you use the conventional methods. So this is where all about the innovation that we have over 100 patents filed in this space in terms of how do you provide a super efficient reliability with energy efficiency for training problems. That's exactly what we are addressing. So one, of course, is the fault-tolerant processing system. That means it's not just duplication. You have to do a lot more intelligent way of providing the reliability with the least cost. And another one is that cross-layer design for efficiency. That means, is it only always duplication? Can I even guess, saying that things are going south? That means they're not going well. If I know it early on, I can probably go to a lower mode of operation. That means instead of running at, let's say, 1,000 miles, I might probably go at a lower speed and probably go and land somewhere. That means, is there a mechanism available by manipulating the cross layer? When I say cross layer, starting from the component level all the way to the your application, are there opportunities to get the reliability required? Because we cannot compromise on the safety and reliability, but we want to innovate in terms of how we can do it optimally. And again, we need to take the approach that is critical, is the system level approach versus component level. We do at the component level, we have our own flip-flop, which is very, very reliable, because we cannot just say that we are going to reliable computing and just do something very incremental differentiation. As I talked about in my first slide, we have to do our only goal is to do a sustainable differentiation. That means when we do it, if somebody the next second best does, it should take few years for them to catch up. Otherwise, as a startup company, it's very difficult to survive. That's exactly what I've done in the past. The same thing we are trying to do here. These are the three approaches that we follow to get that straight line in terms of the system without compromising on the size and the energy efficiency or the scalability. And it's a very, very significant problem. This problem is not something very small one or easy to do. I spent already 5 years on this, 3 years as part of Red Pine Signals, and 2 years post sale of Red Pine Signals. And we still haven't done our first silicon in 5 nanometer. We are a few months away. So we will be taping out the 5 nanometer device on the October 6th. So this is what is my presentation about reliable computing at the edge. And I really appreciate you guys listening to me. Thank you very much. And I'll be very happy to answer any specific question related to reliable computing. Thanks.
We made it. Thank you, Venkat. You had me a little concerned there, but we are good. Okay, this is the Q&A portion of our presentation. So you guys ask the Qs, and our experts are going to provide the As. So let's see. We got a bunch here. We'll go through them. We could probably get to some more. Venkat, what constraints does security put on the reliability of your AI system? And I think we should both answer this question.
Sure. I think, one thing is, Rich, security is a key aspect, not necessarily only at the edge device, everywhere. Security is key aspect. And if you really look at in terms of how the security evolved over the industry, that, it is very, we have a reliable systems today, a secure system today. That's why we're able to do our transaction today. I can, transfer money. I can do all the transactions. However, the assumption here is that the hackers are human beings so far in the whole world. Why this current security systems work is simply because that a fastest computer will take some amount of time. Before that, I change my key. That's a model that we have been living all these years. However, with the supercomputing performance, the computing system that are being available now are going to be there in the near future. You had to imagine that a machine is going to be trying to hack. It doesn't have a 8-hour working limit. It's going to be doing 24 hours. So it becomes super important even at the edge device, even at the endpoint. And when that happens, you need to build the system, security systems into your device, which have to be resistant for those very high performance attacks. So that's where we have within our chip, we have a security processor inside the chip. We call it quantum resistant security assist. That means everything has to be based on non-numerical system, but it's super important to do it. But it puts a lot of constraints for the silicon size. Every time you bring in security, first thing that you have to pay is you have to pay money. That means you have to pay the size. The second one, of course, is very much so in the energy. The moment you increase the size, your capacitance increases, your power increases. And generally, security is something that you have to continuously do on the time. Not only, you switch it on and switch it off, business won't work. So security is very, very super expensive for energy. So that's
okay. How about you, Carlos? You want to take that same question?
So from an AI point of view, security is a major concern because the fact that it's a statistical process means that you can corrupt the algorithm at multiple different levels. One of the things I worked on at a previous company was how to attest to the data set that you're training on all the way through the inference. And I think that's not a solved problem yet. You can use traditional security methods this is a software question more than a hardware question, but you can use traditional security mechanisms to do that attestation all the way through. It's still not fully solved.
Here's a question that I've been asking people. Is there a fear that the bad guys will use AI for bad things to actually hack into the system?
Well, to a degree, they already are. Every tool has two uses, right? It's very cool to have an application that puts your face on a celebrity and have it on your iPhone and you laugh about it. That same thing can be used to create deepfakes. So it is something that the ethics community and the security community have to take very seriously at the very highest abstract level of AI. For the kinds of AI that go on your risks, I'm not worried about it because these are step counters. As Venkat was saying, these are not artificial intelligence in the sense that you think of a Terminator, right? These are things that are helping you have a more joyful experience. The AI is the difference between having an accurate step counter and an inaccurate step counter. So if my step counter gets hacked, okay, I probably over-exercise or something, but it's not.
Yeah, but isn't that like the analogy of who would want to hack my toaster? An entry point is an entry point, no matter where it is, whether it's on your wrist or it's on your set-top box. Once you're in, you're potentially in.
Right, but so AI is a little bit different in the sense that you're actually running a bunch of statistical rules. So it's hard to break. Yes, the runtime can be hacked, but that's a different thing from the model being hacked.
Okay, that's fair. Okay. Okay, let's see. Memory is very constrained at the end point. How do you see this being addressed?
It's a really thorny problem. The more complex models you have, the more memory they're going to consume them, and the memory is used to store the layers, the weights. And so there's research going on in sparsity. Sparsity, right now you have kind of coarse sparsity is easy to compute. Fine-grained sparsity is hard. So I'm seeing some progress there. Also quantization. So it turns out that you used to use 32-bit floating point, or in the case of the speech enhancement model, we use real 64 because you have to preserve space. But then we compress that down to 8 bits and it still works. And now there's research going down all the way to 1-bit compression, binarized networks.
Okay. You want to take that one too, Venkat?
Yeah, I think a couple of more points that I could just add to whatever Carlos mentioned. That if you take the memory, there are two things I would say. One is the size problem. Other one is the energy problem. That means size. You need a huge size, like you mentioned, that you have billions, and because those guys are just going in one dimension, they don't look at the physical side. So that means billions of parameters are there so that I can get some extra accuracy. But realizing that one is what kind of how do we really reduce the size of the memory, because that's super important. And what type of memory you want to realize. Assuming that somehow I solve the problem of size, I can put a massive DRAM, but that comes the energy problem. So that's where I think that non-volatility for solving the energy and some other special memory technologies and algorithms to reduce the size of the memory, because we have to reduce the size. You can't physically do that. It's not practical to do it. Of course, you can say that I need this much memory, but obviously it costs money. If you put infinite money, everything is possible to solve, but that's not engineering. So it's a real problem there in terms of how to solve the size of the memory. So you have to go either approach with the algorithmic approach for the reducing the size, and the type of memory that you have to design to reduce the energy, like that our Carlos mentioned that they use the magnetic memory systems. It's very important to have non-volatility and fast switching on and off.
Okay.
And I should add that MRAM is just ridiculously power efficient, which is why Ambiq chose.
Yeah. Okay.
Okay.
Yep.
Beside TensorFlow Lite, are you seeing any innovation in the AI runtime space? First, you, Carlos.
Yeah, so TensorFlow Lite is super convenient. It's easy to run. Just take your model, compress it down to a TensorFlow Lite model and run it. But it's not super efficient because it's an interpreter. You're running an interpreter on your embedded device. It's probably not the most efficient use of your cycles. So there are tools that will produce binaries out of TensorFlow Lite models. There's other runtimes that are being innovated around micro TVM and PyTorch. There's just a lot of space for innovation here. And to our audience, it's a call to action. Give me a good runtime, and I'll plug it in.
Very good. Venkat?
Well, I think I couldn't agree with any more with Carlos there. Though I do a 5 nanometer chip, we have done significant engineering, designing connectivity in 5 nanometer. All the things are happening, but more than 50% of my team works in exactly the thing that you guys just touched upon.
Very good. Okay, we got
super important.
One more, and this is a similar question. Besides speech, what kinds of inference are you seeing in the endpoint market?
Yeah, so I use speech as because it's an example that people are familiar with. But I would say that the majority of the battery-powered, hyper-efficient endpoint is more time series based. So if you put on a Garmin watch, which is supposed to last months, right? Apple made a big deal out about their Ultras. It lasts a day and a half, or 36 hours. A Garmin is designed to last months. And it is monitoring everything, right? It's monitoring how you walk, how you run, your altitude, your heart rate. It has to do that for months. And so that's a time series inference. We see a lot of that in wearables. I would say a lot more cycles are spent doing that than trying to understand what you say. In the industrial IoT space, we see a lot of anomaly detection and anomaly classification. These are important things. Your fire alarm, figuring out whether it's a fire or not. You don't have to necessarily use AI for that, but when you do AI, you use machine learning specifically in this case. You get a lot more discriminant information out of it. Those are the basic, huge kind of inference tasks that I see at the end. Computer vision, not so much yet. And it's a sensor problem. You know, your watches and your fire alarms don't have cameras.
Right. Venkat?
No comments on that side. I don't have much view, except that, I'm wearing one Garmin, and I'm a very big fan of it because I put my chip in it. That's why.
Me too. I'm a Garmin guy.
Hey, you have our chip too.
I'm not allowed to say, although yes, it does. Okay. Thank you guys. Awesome job here. Thank you to our sponsors for the AI Day Virtual Conference: Acronix, NVIDIA, Intel, DFI, LIPS, Ambiq, Infineon, and Dedicated Computing. We are about to start our second keynote. It's in 2 minutes, so don't go anywhere. As I said earlier, the system will drop you right into the keynote that's being delivered by Google. Good stuff, so stick around. Thank you all for attending, and thank you guys for doing a great job.
Thank you. Thanks, Rich. Thank you.